are already late. So, good morning, everybody. Suresh Chandra Sahab, Mr. Menon, Mr. Jayasilan, Mr. Bajaj, Mr. Gopalakrishnan, all senior officers of Central Water Commission, past and present, and all the participants. Right. We are having this session today with the latest innovations and methods for monitoring dam health.
A very good morning to one and all present here. I would like, I'm taking immense pleasure in welcoming Shri A.B. Pandya. Shri A.B. Pandya is the chairman of Central Water Commission and a civil engineer with MTech in structural engineering from IIT Delhi. He joined the Central Water Engineering Services and has held various positions in CWC and other organizations under the Ministry of Water Resources like WAPCOS, NWDA and NPCC. In his long distinguished service encompassing all the aspects of water resources sector, Sri Pandya has gained all-round experiences in water resources sector involving resource assessment, project planning, design and execution, and operation of safety assurance, funds management, commercial consultancy management, etc. I would like to welcome you, sir. I would like to welcome the co-chairman of this session, Shri Suresh Pandya. He is the former Suresh Chandra, sorry. Suresh Chandra is the former chairman of CWC. He is the very well-known dam safety professional. He is currently involved in a number of dam safety review panels. So it will be very appropriate to have you here, sir. Thank you. I would like to welcome Dr. Arun Menon. He did his B.Arch in Regional Engineering College in Trichy. He did his MTech in Civil Engineering in IITM. And he is a distinguished faculty here. He did his postgraduate in University of Pavia, Italy. And he has been awarded the best outgoing student by the REC. And he is the architect and he has won the Architect Endowment Award for the best architecture thesis in REC Trichy. We would like to welcome you, sir. Thank you.
Thank you for the warm welcome. Now we begin our technical session on the latest innovations and methods for monitoring dam health. It's a very important session. I'll briefly make the remarks on the session, and then we can take up all the papers. There are 5 papers plus one sponsored presentation from the industry. We will take up all the papers one after the other, and then the sponsored presentation, and then we will take the questions in the serial fashion for the papers. The dam monitoring is an extremely important aspect of dam safety surveillance. The dams speak through their behavior. Whatever we did during the design and construction is reflected in the behavior of the dam, and unless we monitor the behavior of the dam in a continuous manner, the change in the health status cannot be identified in time. And this is very important from the point of view of assuring the dam safety. because any changes in the materials that are taking place, any changes in the any other deteriorative effects that are happening are all reflected out of the behavior that is there for the dam, and this behavior has to be monitored through the sophisticated instrumentation. Very cutting edge technologies are generally involved in monitoring the parameters. There are two issues that we always encounter, especially in the case of dam safety assurance and the behavior monitoring. The number one being that the existing status of instrumentation always deteriorates with time. However good instrumentation we do, the dams have to really survive for a very, very long period. And we always observe that after a point of time the instruments start giving way, and your knowledge about the state of stress in the dam, the state of material properties in the dam goes on becoming a little outdated, in the sense that we do not know what is the current state of health in the dam body. And there the instrumentation, especially from the point of view of simulating the behavior, becomes very important. The other part of the instrumentation, which of course we are not really looking here, but the hydrological instrumentation, especially in the catchment area, also becomes equally important, because that is a very great impact on the monitoring of the inflow floods and the capacity and the strategies that have to be adopted for managing those floods safely through the dam, so that the dam is not unnecessarily put to any risk. So all this presents you a very vast and a very, very varied kind of system requirements and a very varied kind of data requirements. The third aspect is the data management, where the historical data has to be adequately stored, analyzed, and kept in a fashion that then can be consumed by the various simulation techniques that are available to us today, so that we are able to understand the current behavior of the dam and accordingly plan our remedial measures. So all these aspects become very important when we look at the monitoring the dam health, and there the technology has to really come to our rescue, and we have to continuously evaluate new technologies for finding out solutions which we can then employ to more and more challenging problems to our dams as they age more and more. Many of our dams, we have a very poor instrumentation record, and we have a very, very poor status of instrumentation in many of our dams, and especially those dams which are also sometimes exhibiting the signs of distress. So how to really take care of this kind of a observational lacuna that we have built into the dam is a big issue that also we need to really address. So with this session, we will be in a position to really understand and have some additional insights into the latest technologies available and latest means available. So I hope that we will have a very good interaction during this session. I would also request our co-chairman, Mr. Suresh Chandraji, also to say a few words.
Thank you very much. The health of the dam is a very, very important aspect. I think I will not dwell on this matter, as you have already been told, and we have heard a lot about that yesterday. I do agree with the chairman that the status of the instrumentation is very poor. But as I have experienced myself, I find that there are many constraints which I have come across after discussions with the state engineers, who are representatives of the dam owners, they don't get the full support which is required for monitoring the health of the dam. Probably this needs to be taken up at a very high level. This is more of a funding problem than the technical problem. And this must be addressed to. I hope the representatives who are attending this meeting here, conference here, they will take up this matter with their higher-ups. Another thing, the DRIP program, which has been started by Central Water Commission, or this is being undertaken under the aegis of Central Water Commission, is a very welcome measure. And at least the 4 states which are receiving the funding, there is a lot of improvement because of that. And I hope other states also will qualify to enter this program and benefit out of that. I think we are already late for convening this session TS4. So probably without taking much more of your time, we should go ahead and start with the presentations. Thank you.
Thank you, sir. We take up each of these papers. We would like to give them 10 minutes each, and I will now call the first paper by Mr. Hiromi Fukuki of the Director, International Digital Earth Applied Science Research Center for the monitoring and assessing reservoirs through e-dams.
Yeah. Thank you, Chairman. It is my great pleasure to be here to make a presentation. Ladies and gentlemen, I was talking about dam monitoring system by using information and communication technologies. So let me talking about my institute, and Sakura is a collaborator of Chennai State. And secondly, I was talking about a project of calling that digital Earth, geospatial information, and we call e-dams, and that are using field server technologies. And I also showing us some small demo and how our technology can help monitoring and assessment of emergency management of dam safety. And also making some concluding remark and short proposal. So I came from Chubu University. It is located in the central part of Japan. And we're setting up a new research institute that called IDEAS. IDEAS is abbreviating International Data Applied Science Research Centers. And last April, Minister of Education and Science and Technology and Cultures designated one of the national joint research centers and usage centers that focusing on the data research. We much concerned about the geospatial technology and also interdisciplinary approach and multi-scale geospatial design for our planet. And we're providing a lot of measurement facility and also related geospatial technology like UAV, and also one of the technology is today I would like to introduce the field server sensor network system. We're also developing some measurement car and also some showroom that are composed by mulch monitoring system. So by using UAVs, we are using that kind of UAV. In fact, yesterday we are using is this Gen HT, taking some slum renovation areas by using UAVs. The resolution is almost a centimeter degrees in there. So it is useful for the environmental management in the dam site as well. Shall we? And also we are using the island site like a Maldives, and it's providing this kind of three-dimensional topographic information. So the data is, I don't know how many people knowing about or hearing about the data concept. That is firstly introduced by ex-Vice President of United States, Al Gore, talking about we need data that is multi-resolution, three-dimensional representation of our planet. It is one of the collaboratory by using this information basis for the collaboration. So ICT can help the monitoring of the dam site and the dam itself. We call this kind of a system is EDAMs. EDAM collecting digital data and digital information, and also providing easy to acquire the data set and analysis and model, and also making updating the information. Later we're talking about such kind of a monitoring system for using the natural dammed lake in Himalayan site. As you know, the global warming effect on the Himalayan region. So glacier is melting and making such kind of glacial lake in the footprint or endpoint area in Himalayas. We would like to monitoring the situation of these kind of a glacial lake by using ICT technologies. So in that case, it is very remote areas and off-grid site. So we're setting up internet connectivities by using digital monitoring system, and also providing a wireless sensor network. And after that, we would like to provide an early warning system for flooding issues, glacier lake outburst flooding. So we introduced this field sensor system. Originally, this field sensor system developed by agriculture ministers. That is they have a need to monitor their field, crop field especially. So field server is like this. You can see in the top of the desk. We'd like to some demonstration after this slide description. Generally, the field server composed of 3 parts. That is providing field gateways. It's providing an access point of Wi-Fi, and also nowadays gateways function by 3G or LTEs in mobile phone networks. And also that is equipped with field cameras, and cameras function observing variation of, especially in this field type, is a crop situation, but also it is usable for the situation of a dam site. And also third part is a field point. We call that is the sensing functions. We can adding 24 sensor network system in this field server connectivities. After that, we have a measurement record like this kind of time series information of the data set. And also, we can do analysis of the cloud services by using some dig information like this. So in the case of Himalaya, we're setting up this kind of wireless connectivities. And this is glacier lake itself. This is end moraine. It's a natural dams lake. In winter season, from November, it is almost frozen like this. We're setting up 2 field servers like this, and to measuring in capturing by camera in the Moraine district, and also full of the range of lake. So as you know, global warming have affected on the situation of this dam's lake. If we have avalanche in an upstream area, or a landslide happen, or a glacier is divided by a big block of ice, so the big surge was happening. So in that case, water level is changed. So by using field server, we connected water level sensors. And if water level changes, to sending a message in the downstream area to avoiding flooding issues. So after that, they providing these kind of the pictures from this kind of field service. And also, they continuously reporting to the record of water level like this. So this is one of the mechanisms of field sensor systems. So I want to show about some demonstration in this field servers. So you can see the field camera in here like this. And you can see in these pictures, and it is controlled by the central office of the management and through the internet. And sometimes they can magnify like this. So could you moving the camera to the like this? So, and also this field samba have a sensor like a temperatures and humidity, and also insulation is like. So this kind of techniques is usable. So let's move on the slide. So the sensing technology is provided by this field servers. In that case, there is a barrierless field sensor record. This is temperatures and humidities and other measurement device. In the dam case, we are equipped with a level of waters, for example. So this is a sensing mechanism. So field server is connecting in an internet network, and also providing this record to the central servers. And sometimes not only viewing the data, but also by using these data for the simulation or early warning system to the crowding systems. So the time is limited, and I will skip and this kind of slide. That is, if we setting up this kind of a network, we can open these data to the public through the worldwide. So this kind of system is a very simple and low cost and low power system, and also providing a multi-mode network capabilities. And by using this, we can providing a real-time data set and real-time simulation for the emergency issues. And also this is providing and connecting the dynamic cloud services. So let's move on our colleague to making some little proposal about just Tamil Nadu areas. So please.
Thank you. My name is Babu Madhavan. Actually, we similar kind of sensor we installed with the help of our Y&M PWD at Pundi Lake actually. And if you have a smartphone actually, please note down this ID 59.181.97.157 / interface. You can monitor the Pundi Dam very clearly by using the sensor. Some of the just show you. Actually, this is the concept actually. So our central office is located, will be located in Chepauk, and you can monitor the 120 dams by using the sensors once it's installed. And right now, actually, we are making a proof of concept by installing this kind of sensor in Pundi Reservoir, Pulal and Chemburammakam Lake. Okay. So this is the what you call sensors actually we installed in Pundi Lake, and by the address actually you can monitor all the temperature, water level, humidity, even surveillance camera. This is one of the pictures I was taken actually recently last week, and some work is going on actually. Even the camera has the what you call option for event monitoring. Suppose actually something is going on the dam actually, you can zoom in, zoom out, and you can also have the face detection applications. And so like this actually you have an interface of Google Earth. Wherever you go actually take your smartphone, enter, log into the site, and click on that icon as a field server. You can have all the eight parameters right now actually. Thank you very much.
So now I call Ms. A. Topple from HR Wallingford regarding her paper on real-time infrastructure monitoring system for dams using artificial intelligence for data analysis.
Good morning. Thank you for having me here today. I'd like to talk to you about our real-time infrastructure and monitoring system for dams, which uses artificial intelligence to analyse the data for you. To start off, I just wanted to go through a background on a project that was the sort of instigator to start the real-time infrastructure monitoring project. It was called the Urban Flood Project. It was a European-funded project that focused on urban flood embankments. So those flood embankments, they were in tight space constraints with high-risk populations. The idea of the project was to create smart dikes so that you could develop an online warning system in order to evacuate if needed, if there was a failure. The project had several partners: TNO from the Netherlands, Cyfernet from Poland, Siemens, the German and Russian part, and STOA, who are the water board for the Netherlands, and ourselves, HR Wallingford. The project had 3 test sites, one in Boston in Lincolnshire in the UK, one on the Rhine Dike in Germany, and one on the Ring Dike in the Netherlands in Amsterdam. We embedded sensors into the embankments, and using the wireless technology, data was transmitted to a real-time continuous monitoring analysis system, which performed anomaly detection and looked for probabilities of failure. If an anomaly was discovered, this instigated the emergency planning procedures, and all of this information could be viewed on multi-touch platforms. So that's where the RTIM system sort of started. But I just wanted to now talk about why we actually do monitoring, and think about how often we actually do monitoring and how much data we actually collect. We gather so much data now with all the new monitoring techniques. The problem we now have is how we actually analyse all that data. It's a lot of data for perhaps one person to look at and assess. So what we're trying to do with the RTIM system is provide an additional tool for the engineers and inspectors to be able to handle these vast amounts of data. So the real-time infrastructure monitoring system provides a bespoke system design for the dam in question. You have qualified panel engineers looking at the dam in question, and they will provide a sensor supply and installation. They'll pick off-the-shelf sensors. They don't have to be any particular manufacturer. They can be off-the-shelf. So they're the ideal sensors for the thing you're looking to monitor. Then once all the data has been collected from the sensors, it's transmitted, and then we use the artificial intelligence artificial intelligence software to analyze the data. The system sets up the IT infrastructure. We look at IT security. This is a big thing at the moment for us in the UK, is the security of the data that we're gathering from these dams. So we make sure that all of the data is secure where it's handled in the cloud using cloud technology. This data can then be linked to consequence models for your emergency planning using the reliable tool, using HR breach, using the rapid flood spreading model, or using the life safety model for the emergency procedures. We can have regular reporting from the system and have regular or irregular anomaly analysis where the anomalies are discovered. So as I've mentioned before, it's bespoke to the actual dam in question. One system isn't the same for every dam. Every dam has its own issues or items that you want to actually particularly monitor. Some of the sensors that we used on the urban flood project included the geobeads. We found these to be really useful. They measured pore pressure, inclination and tilt and temperature. And they were probably about 30 centimeters long, and they could be designed in strands to whatever depths you required. So this is just some of the data that we gathered from the Boston, UK site. And what was interesting, the sensors were very sensitive to change. So the first graph is showing the soil temperature over time, over a year period. And you could see the purple line is one of the sensors installed closer to the surface. The dark blue line is one of the sensors installed further within the embankment. And you can see how the sensors are picking up seasonal change. In the second graph, you've got a image of the tidal level data versus pore pressure. Because although this is a flood embankment, it was a tidal flood embankment in Boston, and it has a 6-meter tidal range. So the green line is the red line is the water level, and the green and blue lines are the geobeads. So the blue line is the geobead at the toe of the embankment, and the green line's the geobead at the crest of the embankment. What we can see is the pore pressures are reacting with the tide, as you would imagine. But what we don't see is that there's actually a time phase between the green and the blue line. Now, this is something the artificial intelligence can pick up. So with the data in the embankment, we can wirelessly transmit the data to the secure Siemens server, which is where the AI is doing the analysis. If there is an anomaly detection, so if you think back to the last slide with the tidal levels, if that time phase lag increased, you'd probably have a sign of potential failure. This is where the artificial intelligence will set off the early warning system, and on your desktop or your tablet or your mobile phone, you'll have an alarm raised. And that will initiate an anomaly investigation by HR Wallingford and Siemens. What Siemens will be doing is looking to see why the AI has identified an anomaly, and it will talk to ourselves, and we'll look to see whether that anomaly is actually normal behavior. If it's normal behavior, then we can amend the AI to understand that this is normal behavior of the dam. Whereas if it's not normal behavior, then we can initiate the alarming system. So I keep talking about AI. I'm going to try and go into a bit more detail about that now. So artificial intelligence is trained by experts undertaking traditional engineering analysis alongside the AI anomaly detection. If deviations from the reference state detected, the AI will flag exceptions and raise an alarm. So the AI has the ability to look at relationships between sensors, not just the sensors themselves. For example, if you had a high water level and you've got higher drainage flow leakage, then you probably wouldn't be too concerned. Whereas if you had a low water level but high drainage flow leakage, then you would be concerned. The AI has the ability to recognize that as abnormal behavior and detect an alarm, not just the high-low level alarm, but alarms with comparisons between data. It can look at the different types of sensors, and it can look at the dependency within all of the sensors within the cross-section of the dam. These are just some screenshots of the desktop. This desktop screen can be designed as to how you want to see all your data. The system's also flexible that you can add other reservoirs to the data and to the system. Here's just a close-up. You can see we've got just the mapping, so you can click on your dam. If there was an alarm on your dam, that would appear red. So you can quite quickly look at your data screen and see whether there's any issues on your dam. So what are the benefits of having a system like this? We have enhanced surveillance. You may have dams in remote locations that you can't actually get to in severe weather. Having eyes on the ground when you can't get to that dam is a powerful tool. This improves safety, and also it improves and safeguards corporate reputation. If you can ensure that your dam is safe when you can't even see it, that will safeguard your reputation. For the engineers themselves, it allows the data to be in one place. So data from different sensors, different manufacturers are all in one location, rather than having to go to various different sites. Not only that, you've got an extra pair of eyes looking at your data. It's actually analysing it real time, every second as it's taking readings. So just in summary, it's holistic and bespoke design based on the site needs. It's continuous monitoring. It's user-friendly, and it uses combined engineering knowledge of HR Wallingford and the IT experience of Siemens for anomaly detection, with secure data handling and a standard level of anomaly investigations included. Thank you.
So now we have case study on water quality and lime leaching in dams by Mr. N. Pandian, Executive Engineer, PWD Chennai.
First one. Good morning to everybody. First of all, let me take this opportunity to thank the authorities of CWC, IIT Madras, particularly PWD, for having given me a chance to present this paper in front of this highly organized forum. And I'm N. Pandian, and I've been working in this department, PWD department, for the past 32 years in various capacities. At present, I'm working as Executive Engineer, SM&R Division. Of course, health status of the dams can be monitored by so many methods. As you all know, by instrumentation, by geophysical methods, and the last one is water quality and lime leaching method, which is being carried out by us in PWD. Our soil mechanics division, research division, has been allocated with the work of monitoring the health status of the dams, important dams in Tamil Nadu, by carrying out these water quality and lime leaching studies. Of course, till 1984, these studies were confined only with the major 3 dams, Periyar, Vaigai, and Manimuttar. Of course, gradually, this study has been extended to 14 other major dams of Tamil Nadu PWD. Of course, based on the quality of the waters, the reservoirs, 14 reservoirs of Tamil Nadu have been classified under 3 categories: a reservoir with hard waters, a reservoir with moderately hard waters, a reservoir with soft waters. In this first category, we have got 4 dams: Metur, Krishnagiri, Satanur, and Vardhana. And a reservoir with low hard waters, that is moderately hard waters, we have got 3 dams: Vaigai, Amravati, Bhavani. Of course, the last one, reservoir with soft water, mostly these dams have been located in the hilly regions or at the foot of the hills: Periyar, Pechiparai, Perinjani, Manimuttar, Paramikulam, Sholayar, Lower Nerar. All these dams are having low pH and low TDS. Actually, these are classified under aggressive dams, which can be dealt at a later stage, which will cause more lime leaching. Of course, special cases will be, then and there will be referred to SM division for carrying out the research studies. One such case, recently, field people have reported that they are finding it very problem in the operation of the shutters in Kodakanar Dam. Higher authorities have referred this problem to SM division, and the then executive engineer have deputed the staff to the Kodakanar Dam, and they have carried out the study, detailed study. Of course, the Kodakanar Dam starts from the Pine Hills on the western Ghats and it runs to 104 kilometers before confluencing with river Amaravati. Of course, the dam, Kodakanar Dam, has been located at the 64th kilometer of the Kodakanar River. Actually, initial preliminary investigation reveals that the Kodakanar River is not having the natural surface water. It is contaminated with highly industrial pollution. And of course, our staff have collected water samples from so many places. That is from Athur Anakat, Athur Reservoir, Sitalagundu Tamrakla Anakat, Budipura Anakat, Kodakanar Anakat, Venkatrama Anakat, Lakshmipatti Anakat, Budipura Anakat, Kodakanar Dam, downstream of Kodakanar Dam. They have collected water samples from all these 10 places and they have tested, they have carried out the test both at site and as well as at the lab. And it showed that pH values ranging in between 8 to 9 and the waters are polluted with heavy pollution, that is particularly industrial pollution are latent to this river Kodakanar. An initial observation, deposits were found all over the shutters and structures. Scaling has been formed throughout the structure. Shutters are completely corroded. You can see the photographs of the Kodakanar gates, shutters. The shutters have become almost mobile. That solid shutters have become almost mobile. That is due to the chloride attacks. And you can see that test results have been of the 10 places, samples collected from the 10 places have been plotted. You can see 2 places where the TDS value has gone above 6,000. Normally the reservoirs will be having TDS less than 1,000 only. All our reservoirs, 14 reservoirs are having TDS less than 1,000 only. And here the Kodakanar River, Kodakanar Dam is having water with TDS more than 2,000. That is the problem of this shutters, non-operation of the shutters. Of course, when the test results of the Kodakanar Dam has been plotted over the Baylis curve, actually Baylis curve can be applied for waters with high pH and high TDS. Of course, Langmuir index can be followed for low pH, low TDS, particularly where S is less than 1,000 parts per million. Here, Kodakanar River is having high pH and high TDS, so we have followed the Baylis curve. You can see that Kodakanar Dam, that value is tested value of the Kodakanar Dam is falling above the safe band. This is the safe band. This is the safe band. If the values fall within this band, then the water will be very, very safe. Actually, the Kodakanar Dam, the values of the Kodakanar Dam is falling above the safe band. It means that the dam is having scale-forming water. That's the reason why the shutters have become more thick. They were found in operation of the shutters. They have found some problems in the operation of shutters. The conclusion, the entry of polluted water shall be stopped. Shutters can be coated with special type of coatings. Existing surplus arrangements with shutters may be replaced with shutterless arrangements, that is uncontrolled spillway. Let us go to the case study, lime leaching study from Manimantwa Dam. In the beginning, I have said the reservoirs have been classified under 3 categories: reservoir with hard waters, with moderately hard waters, and with soft water. Here, in the case of lime leaching studies, the reservoirs can be classified under 2 categories. That is, non-aggressive dams and aggressive dams, based on the LI index, that is Langmuir index, which can be calculated based on the 5 parameters: PS, TDS, temperature, total hardness, and total alkalinity. And of course, we have plotted the TDS of 14 dams and LI of 14 dams. We are trying to establish that there is a definite relationship between the TDS value and the LI. We are trying to arrive at a thumb rule based on which the field people can arrive at a conclusion whether our dam is having aggressive water or not. You can see that is TDS is directly proportional to the LI. If the value of the LI is minus 1.5, that will be coming under the category of non-aggressive dams. All the dams which are located in the plains will be having high pH and high TDS. They will be coming under this non-aggressive dams. As far as the lime leaching is concerned, aggressive dams where the value of the LI is less than minus 1.5 will be a case of concern which will cause more lime leaching. Here, non-aggressive dams. In non-aggressive dams, 14 reservoirs, Metur, Krishnagiri, Satanur, Mordana, Vaigai, Lower Bani. These 5 dams are coming under this non-aggressive dams. That is, dams which are located in the plains. Dams which are located in the hilly region or at the foot of the hills. Say we have already seen the dams with soft waters. That is with low pH and low TDS. They are more aggressive dams. Amaravati, Periyar, Pechipare, Perinjani, Manimuttar, Parambiru, Sholar and Lower Nerar. And of course, lime leaching process is a complex phenomenon. We have tried to explain this lime leaching process in 6 stages based on our past experience and theories. You can see stage 1. Here in this stage, that normally the water stored in in dams will seep through the dam and it will be collected in the drainage gallery. And the figure 1, stage 1 shows the position of the drainage shaft, which is very clear. No deposits were found. This is the stage 1 of the lime leaching process. And in this case, NaOH, that is sodium hydroxide and potassium hydroxide will be coming out. In stage 2, the color of the seepage will be white, pH will be in the range of 13 to 12.5. In this case, the calcium oxide will be coming out. Here, that stage 3. Here in this, the seepage water will be having creamy white in color. In this case, the calcium oxide will be coming out, little of alumina and little of iron oxide will be coming out. In stage 4, the first one is the starting stage of stage 4, and the second one is the last stage of the stage 4, that is advanced stage of stage 4. That is, the seepage water will be yellowish in color, the pH will be in the range of 12 to 10. In this case, the more alumina will be coming out and less iron oxide will be coming out. This is the stage 5, advanced stage. All alumina, less alumina, the balanced alumina will be coming out, and the more iron will be coming out. Of course, the silica gel also will be coming out. That is the stage 5. The stage 6, where the dam structure is not at all having any binding materials. Fungus have started growing in the vacuum, in the voids created in the structure. That will be coming out. That is the last stage. And of course, the cumulative loss of lime loss has been calculated for the Manimuttar dam. The total loss is 4.88%. Of course, allowable limit is 15 to 20%. This chart have been plotted. That is, whereas the V9 block has shown the cumulative loss has occurred in the more losses has been occurred in the V9 block, and you can see the photograph on the left side. That has been taken inside the gallery. That has confirmed our result. Actually, you have to give more concentration towards the dams which have been located in the hilly regions. That is a case of concern. Thank you.
Thank you, Mr. Pandian. Now we have assessment, instrumentation and management of dams by Matthew Pavilshak.
Thank you very much. I'd like to thank the organizing committee and the session panel for the chance to share our experiences with this group. I represent the diagnostics group within Walter P. Moore. We're an international consulting engineering firm with local offices here in Pune. The diagnostics group, we specifically focus on helping owners and asset managers assess, repair, and maintain their assets over time. The topic today, I'll step through the methodology that we use to conduct assessments, long-term monitoring, and capital asset management plans for our clients to help them understand the financial needs of operating their assets and the trade-offs between different management strategies. Thinking about this process, it's really a continuum, starting with an initial assessment, implementing repairs as necessary, monitoring over time. That's where the structural health monitoring comes in to help us understand if the structure is performing the way we think it is, or if there's changes over time. And then getting into a management strategy where we're proactively anticipating the needs of the structure. Many of the deterioration mechanisms that we see in dams and other structures are material in nature and are very predictable based on previous experience. And so we use different models to predict when new interventions will be necessary to help clients project forward and understand what the needs of their asset will be over time. So of course, we always have to start with a global assessment to understand the current state of the dam, making sure that we're looking at it holistically, looking at not just the main structure, but also the mechanical works, the apertures, the surrounding abutments, to understand what the vulnerabilities are, what the deterioration mechanisms we're seeing, whether we're seeing any signs of active deterioration. And then moving on from that, especially in reinforced concrete or reinforced masonry construction, once we start to see these deterioration mechanisms, is to quantify them, to understand the severity. Certainly, we're always looking at corrosion and spalling, leaching, things like that. We also often see these deleterious chemical reactions in concrete, your ASR or DEF. Understanding the extent of that and how severe the issue is within your structure is very important. When we have jointed construction, a lot of times understanding how those joints move over time is crucial to understanding the behavior of the structure. We employ non-destructive evaluation on nearly all of our projects because there's only so far you can get with a visual review. You're really scratching the surface. And so there are many types of non-destructive evaluation techniques, and I've included some of the most common ones that we use, particularly in concrete and masonry dams, although there's plenty of others. Thinking about one of the most versatile tools for understanding near-surface deterioration is GPR, sometimes called surface penetrating radar. And this is a tool that's relatively affordable and easy to use, and allows you to characterize many things about either a reinforced concrete or masonry structure, helping you understand reinforcing patterns, delaminations, and voids, and understanding the depths and the extents of these distresses. What we often find is that what you can see on the surface, what is visually apparent, is usually only a fraction or the tip of the iceberg of the distress that's latent within the structure. And so by doing these evaluation techniques, we can extend the knowledge and get a better sense on the scope and the potential cost for when we move to a tendering process. GPR is, like I said, a near surface technique, but also in the spillways and other related works, you can often see through the thickness of the member, and you can also determine undermining and voids. I've included here also impulse response and acoustic tomography are both two methods that are similar in nature, but work on different levels depending on whether you're looking at a mass concrete structure or whether you're looking at surface issues. But essentially the fundamentals are the same in that you're imparting a compressive impulse wave into the structure, and you're using an array of sensors to measure the arrival of that impulse at the receiving locations. By doing this iteratively over a matrix of points, you can plot different parameters such as mobility and stiffness within the structure based on the different arrival times of the signal to different parts of the structure. By doing that, you can estimate cracking, you can determine anomalies within the structure. And so if there's particular areas where the wave speed is much slower, it can be indicative of voids or cracking, things like that. And so this tool can allow you to look through quite a large thickness of concrete with the acoustic tomography, although you do generally need access to more than one side of the structure in order to accomplish that. So that can be an impediment to it, but impulse response can usually be done on one surface, but will give you more of a surface profile. Once we've completed the assessment, it's important that we understand the long-term health of an asset. With dams, many dams have instrumentation included in the initial construction, but those sensors go away over time. And so one of the things that we always recommend is including a new instrumentation package. And I've included some of the most common types of instruments that we use, although there's certainly many others, as some of the other presenters have discussed. But this long-term monitoring is relatively affordable, and it's easy these days to set up alarm situations where you can set parameters and you can get notifications about changes in state. Certainly for many types of dams, inclinometers and tilt meters are one of the most common sensors. We can obviously mount them down borehole is kind of the most common arrangement. In some concrete structures or masonry structures, if we're worried or if we're concerned about movement or rotation of certain elements, they can also be effective mounted on the surface, which is a much easier installation process after the fact. Certainly, as some of the other presenters have mentioned, we want to measure all of the known factors which may influence the data, such as temperature and water height, and maybe some other parameters depending on the structure, because you want to be empowered to understand how these cyclical changes in the measured data relate to known phenomenon. So we know when we install these sensors that we will get seasonal variations or even daily variations with temperature. And so if we don't measure temperature, it's hard to make that correlation. Of course, piezometers are very common for measuring soil pressure and to understand how water is interacting with the subsurface soils. Whether or not if we see large changes, then we know that we're seeing changes in deterioration mechanisms. And strain gauges, I've included a few samples here. There's many surface-mounted options for installation after the fact to help you understand how strains are changing within the structure. Then moving on, I want to talk a little bit about capital asset management plans, which are kind of the tie that allows an owner to move to a proactive management technique. And the goal of a capital asset management plan is to understand the existing deterioration and the mechanisms in play, to use engineering experience to predict when future interventions will be necessary and the type of durability enhancements that will need to be done periodically, such as repair of spalls and other durability enhancements that can be predicted and projected, and then understanding what the expected quantities will be and understanding what that expense model will be every year for 5, 10, 15, 20 years to help the owning agency understand what the cost of maintaining their asset in an optimal way will be. And that allows clients to then work on a funding model to understand how they'll be able to implement that. And as part of this, we often do life cycle cost analysis to help people understand what the benefits may be of selecting a more aggressive repair approach up front, which may lead to further savings down the road. So as I mentioned, once we have the expense model that empowers the operator or the owner to work to budget towards those projected expenses. And then, of course, like anything, we need to maintain and update the plan over time. And so these capital asset management plans are intended to look forward 10 to 20 years. And as we do periodic assessments and receive the feedback from the monitoring systems, it's important that we revisit those plans every 3 to 5 years to incorporate the new data that's been obtained from further assessments or from the instrumentation to adjust the assumptions and to project out into the future more accurately. With that, I thank you for your time. Thank you.
Thank you, Mr. Matthew. And now we have Dr. Rajbal Singh with the dam safety instrumentation with case study.
Good morning, everybody. I'm going to talk about a case study of dam instrumentation at Tala Hydroelectric Project. Dam instrumentation is generally done for the dam, safety of the dam during construction, and it's very important to have the instrumentation in place during first filling, and then we should do it throughout the operation. Based on the instrumentation, we can do some refinement in our design. We did some refinement in the construction also, as I'll be talking about it. And the data can be utilized to do the back analysis, as our input parameters to our analysis and design are not properly done. So I think I should not talk about the number of dams, but generally instrumentations were remembered in the old days whenever some problems are there. Even now also, even if we are not doing a good instrumentation, we definitely remember the instrumentation whenever some problems are there. And most of our projects these days are very well instrumented. So this project is 3 kilometers downstream of Chukka Dam, constructed by Government of India, and this is the dam, then this is the headrace tunnel. I don't want to do this. This is the Wangchu River in Bhutan, where this project was constructed. Except dam, all the components of the projects were underground. So it was a 92-meter height with a 130-meter length at the top. And this is the dam photographs after the completion of the dam. This is the reservoir filling. This is the downstream of the dam during construction and during operation. It's not moving. This is a reservoir filling. For doing an instrumentation program at Tala Hydroelectric Project, we planned this instrumentation program just before the start of the construction of the project. We prepared the technical specification for the instruments, and then first time, I think, in our hydropower construction, we had a contractual arrangements for calibration, supply, installation, and monitoring of the instrument. To see the accuracy of the data, actually, we should plot all this data, and it's better to go and check the data whether you are getting it accurately or not. And then you should do a continuous analysis of the data. Unless you do that, you keep on collecting the data, then you will not be able to find the fault with your instruments. And it is always better that we prepared a documentation report, which was done at this project site. And after the completion of all instrumentation work, the all instrument should be clubbed with the data acquisition system. The instrumentation is again dependent on the attitude and interest of the management. Sometimes they give more preference to the construction activities than the instrumentation, and we definitely remember it again at the time of some point. And there should be somebody responsible for the instrumentation at the project site, like Bhakra Dam, they are having a dam safety unit. We should have this dam safety unit. Now we are having a dam safety directorate in CWC, we are having in all the states. So it's better that we have the dam safety unit from the first day of each dam. And as far as cost of the instrumentation, some people worried about it. It's not much. Always in the estimate as per CWC guidelines 3%, but at this project site it was only 0.23%. So we should never worry about the cost of the instrumentation. This Tala Hydroelectric project was constructed with a cost of 4,321 crores, and the project was fully financed by the Government of India. It was constructed with the Indian technology. We were not supposed to call any foreign experts, and we are getting all the electrical supply from the. We had a contractor, Encarderite Electronics, and this contract was awarded to this contractor just before the start of the construction, and they were giving us the monitoring results, and then I was preparing the report. These are the instruments: temperature meters, pore pressure meters, joint meter, crack meters, multi-point borehole extensometer, normal plumb line, inverted plumb line, concrete pressure cell, vibrating wire strain meters, uplift pressure pipe, strong motion oscillograph, automatic water. These are the instruments. And out of 282 instruments installed at this project site, 277 instruments were in working stage during the construction. This is the success of the instrumentation is this project site, and this was only possible because we had a separate contractor for this. And at the time of installation, our engineer in charge, who is sitting here, Mr. Vinod Verma, I was in charge of the instrumentation, and a person from the contractor side, we used to be there. And if you install the instrument, you put the first layer, cover all the instruments with the first layer of the concrete, then you should not worry about it. We should take care of the instrumentation. Only 5 instruments were not in working order. One was some fault with the instrument, and 4 instruments were not working because of the water leakage problem. So the instrumentation was done in block 2 and 5 of this project. And block 2 was the non-spillway block, and we had the set of instruments, temperature meters, different stage, and all this instrument actually, stress meter or pressure meter, thermistor is inside in all vibrating wire instruments. So we should not have this, we can reduce the number of instruments by not installing temperature meters separately here. So that is my suggestion. Then these are the galleries for the instrumentation. This is a overflow block where we had a set of instruments. And this is I come to the monitoring data. I joined this project in April 2002, and this data was already available. I got this data plotted, and I was surprised that our placement temperature of the concrete was only 10 degrees centigrade, but in our plotting, I got it around 30, 31 degree. And then I asked the contractor, why are you getting this data? So they started doing the monitoring after 28 days, and which is not a correct procedure. So I asked him in future that you better do it from the day 1, so that when you are placing the concrete, you are measuring the data manually, and then you can take the reading from the instrument also. So that shows you the calibration of the instrument also. So this temperature went up to 31 degree, and it got settled somewhere around 22 degree in this case. From the next set of instrument, we started doing the placement temperature, and then temperature rises, and maximum was 16.1. This was because of the reduced cement content in the mass concrete. Sorry. And you can see it here, the temperature was 10 degree was placement temperature. Because of the low ambient temperature of 4 degrees centigrade, the temperature came down, and then it went up and it got settled around 13 degree centigrade. So these are all the readings of the temperature meter. And based on this temperature data, we got the cracking in the dam. And we knew that this cracking is coming because of the higher cement content in the mass concrete. So we started reducing this cement content in the mass concrete from 210 kg per cubic meter to 140 kg per cubic meter. We reduced it, and up to 190 kg per cubic meter, we were having this cracking in the dam. We were monitoring this data also, and after 180 kg per cubic meter of cement, we were not having any cracking in the dam. And based on this data, we reduced the cement content from 475 to 425 kg per cubic meter in our headrest tunnel also based on this data. Because here we were doing, and we were not having any compromise by reducing the cement content. You can see this, when cement content was 180, we got the strength of the concrete. After 410 days, it was 43. And after that, we were not getting even increase in the strength. We were getting the reduction in the strength even by increasing time. So this is the kind of data we can get from this. This is the pore pressure meter. We got the reading up to 4. Then the stress meter, we can see this. As the construction stages were increasing, our stresses in the dam were also increasing, and we got the stresses maximum 5.5. This is the strain meter data. We had the plotting of this data. I prepared 6 reports during my stay at the project site for about 5 years. And these reports contained the detail of the instrument, installation of instruments, monitoring of instruments, conclusions, all plotting in figures, and annexes contains all the data, all routine data available at the project site. So the conclusion of my is that we could reduce this cement content in the mass concrete, and cement content in mass concrete should be optimized to achieve required strength, and high cement content leads to cracking in the mass concrete. Temperature reading should be monitored from the time of placement of the concrete so that you can have the calibration of the instrument also. I had this stress is 5.5 to 4.4 kg per centimeter square based on the height of the concrete over this instrument. And the only data I could get from a FEM analysis done by IIT Roorkee, that stress is from static analysis was 9.2 kg per centimeter, from dynamic analysis was 12.6, but our stresses were within these limits. The safe design parameters must be made available and may be attached with the data acquisition system as alarm for further monitoring of the safety of the dam. This data was not available to us. So whenever we are issuing the drawing for the instrumentation, those drawings should have the safe capacity of temperature, stress meter or strain meter. So designer should provide that data. In general, the behavior of instrument installed at this project was seeing the increasing and decreasing trend was observed. A record number of 277 instruments were in working order out of 282, and this was possible only due to the awarding of contract for supply, installation, maintenance, and monitoring of the instrument before commencement of this. These are some of the instruments. My predecessor has already discussed these instruments. So I think this is one of the most important equipment, inclinometer. I think we should use it for a concrete dam also. This is a very effective instrument. Okay, thank you very much.
Thank you, Dr. Rajbal Singh. Now we have presentation by a sponsor, Mr. Julian Gray, regarding products and services of Mrs. Trimble Navigation, India.
Good morning, gentlemen, ladies. Some of you might recognize my accent as coming from South Africa. So a moment's silence for us losing the cricket yesterday. We're most unhappy about that. So we're hoping we actually thought it would be a South African-Indian final. Not to be. Sad. So now we just wait for next week. What I'm going to do is I'm going to introduce to you the monitoring system that we have designed in Trimble, specifically for dam monitoring. I started dam monitoring in 1981, a long time ago. One of the early presenters yesterday was talking about slide rules and seven-figure logs. I hate to tell you, but that is what I started with. I don't think there are many people in the room who did that. Anyway, we've got a monitoring system that we've installed in many dams throughout the world, and I'd like to show the monitoring system to you so that you can see how it can apply to the drip project. I'm representing our whole team that's here today, so I'm just the voice for the Trimble guys who are in the back here, our Indian representatives who are just really great guys. Certainly know how to feed me, that's for sure. Okay, let's kick off. What is our total system that we are offering you? First thing we start off with is a dam. It sounds straightforward, but this is the structure that we are going to monitor. What we do with that dam is we put sensors on it. Now, I've shown representative sensors of the type of sensors that we use here. The top one is a GPS sensor, GNSS, it measures position from satellites. The second one down there is a total station, which does optical measurements. It's an automated instrument. You program it, it stands in the sun, and it works on its own. The third one there you see is a seismograph. It's a seismic instrument, measures seismic activity. And the final one is a representative geotechnical sensor. Now, our system is designed in such a way that we can take any form of geotechnical sensor input. So all the sensors which have been shown in the previous presentations here, we can acquire the data from those sensors without any problems, including the cameras from a system like this one in front of us. Very nice system you've got there, by the way. Very nice. We capture data from those sensors at various rates. Now, these sensors I've shown here are essentially automated, but obviously we can capture data by old pen and paper, which I'll cover in the next slide or two. We capture the data from those and we feed it into a software system. Software system has a centralized database in it, which addresses the one problem that was raised earlier on at the start of the session about data management and data storage. Obviously, the historic data gets captured in this database and kept there for analysis and viewing. That data is then available via a web interface in various forms throughout the environment which is being used to monitor the system. So what I've shown here is the system installed on a number of dams with all the data being observed. If you look carefully at those little boxes, you'll see that the data is being observed via the web interface on the dams themselves. So each of those dam operators will be looking at the data which relates to his particular dam. But the data is also available at the headquarters or at a centralized location. Now, it's not necessarily a centralized location, it's just simply any location that can have access to the internet. If I was very brave, I would actually pull out a tablet and show you a live system that's running at the moment, but of course we all know what happens when you do demonstrations. The moment we bring out the tablet, the internet will go down. So I'll tell you that it does work, and if you're interested in seeing the live demonstration, then just come to us afterwards and we'll show you the web address to go and have a look at a live installation on a dam. All right, I'm going to deal with the various components that I showed you in that previous slide. So if we, first of all, our system can access all dam types. So there's no limitation as to the type of dam that we're looking at here. The dam is a structure that we are measuring. So it doesn't matter what type of structure it is, whether it's an embankment dam, a mixture between the two, or a concrete dam. We have no problem measuring the thing. I'll now run through the various type of sensors that to start with, that Trimble provides to you. We provide GNSS receivers. We have a specific receiver designed for the use on dams. It is a smaller version of the one that you see there. It's designed to be affordable, and the idea behind that is that you take the normal amount of money that you would spend on a GNSS receiver, and you would have more receivers, so that we can increase the amount of data that you would get using GNSS receivers. We have optical total stations. Now that instrument that you see on the right-hand side there is a Trimble S8 instrument. That instrument is totally robotic, so it's controlled completely by the software. There's no human intervention into it. We monitor, obviously, the data that's coming from it and the data flows that come from it, but we program it to observe the targets, either the targets that we've pre-placed, which are prisms, or directly onto the surface of the wall. And we can program that thing to run at various intervals during the day. And we can also instruct the instrument to increase the amount of observations that are being taken in the event that we see some form of anomaly, either on the wall in total or in a specific area of the wall. We then have seismic equipment. I've shown three forms of the equipment there. The bottom two are standard seismographs, seismic recorders. The yellow device is something which has just been released quite recently. It was in fact, we had a release of this instrument 2 weeks ago here in India. It's a combined GNSS seismic instrument, which allows us to get positional accuracy, position determinations at a rate of 200 hertz with high accuracy. So we can actually get positional determination of the wall during any form of seismic activity. Very fancy machine. It allows us to do harmonic analysis of the structure. I don't go into it in great detail in the slide. In fact, that's all I'm going to show about it. But if you're interested, it's a very unique instrument. Come and talk to us and we'll tell you a little bit more about it. The final set of instruments that I've got here are geotechnical sensors. Now, I literally ran out of space showing the type of sensors we can have here. So in the previous presentation, there was a very nice list of geotechnical sensors. We can read all of those. So all of that information can come into our system. So what we've designed is we've designed a system to capture data, and it's really source agnostic. So we don't mind where the data comes from. Fine, what do we do with the data when it gets into the database? We have to observe this thing. We have to actually look at it. So we have three levels of software that we present to you. We have a web-based, it's really an entry-level piece of software which is designed for the small dam operator who cannot afford to have a sophisticated monitoring system, but needs a place to store his data and visualize his data. And this is a software package we call T4D Lite. Our main package is called Trimble 4D Control. There is a desktop version of this, which is based on a server, or a cloud version. Now, the type of version that we're looking at for the DRIP project is definitely cloud-based. Based on the number of dams that we are looking at here, we're anticipating one owner having a number of dams that he wants to monitor, and monitoring 100 dams with this system is certainly not a problem. That is the heart and soul of our system, and that's what I will cover in the next few slides. And then finally, we have really scientific software, which is the seismic analysis software. This is designed for post-event analysis of the data which comes from our seismic sensors that we have on all of the dams. Now, the whole of India is classified as a seismically active area. So in all the dams that we are looking at here, we have some form of seismic sensor included in it. So those are the primary three software packages that we have on offer. And the one that I'll cover now in detail is the one in the middle, the Trimble 4D control software. Now, the software itself comprises two parts. It comprises a very powerful backend, which is a powerful engine that does a lot of number crunching and a lot of analysis. That part, I just want you to know, exists. You don't have to worry about it. It sits in the cloud and it does its thing. The thing which is important to you is actually the usability of the data. And that is the front end, the interface that we present with it. And what we do here is we present a web interface which is designed for two things. It's designed for easy access and easy use of the data for normal day-to-day operations. And then it's designed to have a second component to it, which is the complex analysis of the data in the event that some form of activity is detected. Right, so here's a screenshot of the web interface. Each of those buttons takes you off to a particular zone of interest, and I'll touch on a number of them to explain to you what this software does. If I can get to the next slide. Okay, the first thing is to show the data in a spatial context. So what we do here is we have icons which are color-coded as to the state of the sensors and the state of the data that is coming from it. Positioned on, in this particular screenshot, it's a Google map, but we use any form of map background. And you can see the icons of the sensors on it. This is a dam which is in southern Africa, and this is the one which we can actually show you live. We have permission from the dam owner to show you this data. And the color code of the sensors actually indicates the status of those sensors, whether they're in an alarm condition, whether data is flowing or not. If you tap on the sensor, you can get information relating to it. We can also show the sensors with an image background to them. So if we have a cross-section of the dam, we can show the sensors in relation to that cross-section of the dam. We have a simple form of charting, which is totally interactive. And these charts get updated the moment the data comes and is available. We have complex analysis functionality on this software, which uses Boolean comparators, where we can compare data from different data sources. We allow the creation of composite views of data so that you can look at multiple data sources in one screenshot. We have very complex alarming facilities on this. So we have alarming functionality which allows for standard alarming, alarm escalations, the issuing of SMSs, emails, the firing off of batch files, activation of audible and visible alarms, etc. And then finally, the one overall screenshot that we have here is a control room environment screenshot where we summarize the status of each dam in one screenshot. So you can have a screen like that showing the dams in a particular area, and each of the icons on that screen represents a particular dam and the overall state of that dam. And if you click on that icon, then you will go directly to the web interface relating to that particular dam. We have a proposal on the drip solution here where we will offer to evaluate your dam. We will come and design a solution for you. We will provide manual collection facilities, and we will actually run it for you if you so wish. Now the guys in the back here are here. We have all your contact particulars. If you don't see us, we will see you. So we will be in touch. We will certainly show this system to you, and I can say that it has been deployed in more than 40 or 50 dams throughout the world very successfully. Gentlemen, thank you very much. I thank you for the opportunity of presenting this. Thanks.
So now we have, of course, eaten up 15 minutes into our tea time, and we can quickly have a round of questions in the serial order in which the papers were presented. So I propose that we give about a total 5 minutes within which we can conclude our question answers. And we have, for number 1 paper, monitoring and assessing reservoir through E-dams. Is there any question? Yeah, please. Be brief, because we have to conclude all the 5 papers in about 5 minutes time.
Yes, so thank you, sir. I am very delighted to see that so many latest instruments with the advent of this telecommunication technology and web technology have come off, and I am confused whether any standard will come off to utilize these instruments for our upcoming dams. And regarding the first presentation, I would like to know, they told that one unmanned vehicle is being used to take the photograph, three-dimensional photograph, and that can detect the cracks and cavities in dams. I want to know whether any such vehicle is available for underwater survey for cavities in the upstream.
Yes, sir. There is another drone called underwater drone actually that give you three-dimensional bathymetric topography, sir. It's available. You can just carry in a small briefcase and you can install in a small boat, and whatever the stream width, you can go there and you can do this, sir.
Thank you. I think we already have one remote operated vehicle at CSMRS for the underwater inspection.
Yes.
So there are a number of such products are indeed available which you can use for different depths and different kind of turbidity in the water. So now we'll have second paper, real-time infrastructure monitoring for dams by the HR Wallingford. So any questions on that? We'll move to third number, the case study on water quality and lime leaching in dams. It was a very interesting paper.
Yeah. Very interesting study. I have two observations. Perceptions are very important. Moment you classify aggressive dams and non-aggressive dams, it sends a different kind of perception. So that should not be the way it should be classified. The way of classification which you have used is a 1935 Langelier index. But I would just advise on 2 points. One, please look up IS 456 2000 edition and later. It's one of the most advanced ones regarding classifying the aggressivity of the environment in which a concrete dam stands. So do not classify as aggressive. It sends a...
Your points have been taken, sir, well taken. Actually, aggressiveness is, as far as the lime leaching is concerned, I'll clarify it very clearly. Lime leaching, as far as the lime leaching is concerned, we have classified like that. Nothing else. Thank you, sir. Thank you, sir. Your points have been well taken.
Another is, there is an ICOL publication. You look at it, you will have a better perception of how to do this. With enough data which you have collected, you will be in a better position. In case you want some help from us, we will help you.
Yes, sir. Yes, sir. Actually, we are the pioneer in this lime leaching studies, and our studies have been confirmed by the CBIB publication. Actually, we are the pioneer in this study, lime leaching study, and this methodology has been confirmed by the guidelines for measurement, testing, and analysis of seepage from masonry and concrete dams by CBIB publication. Okay, so thank you, sir.
Yeah.
Thank you very much, sir.
Only one good thing that was there in the paper was, the correlation of color and composition of leachate with the possible residual strength and competency of the material. This is something which is good. So now we move to the paper number 4.
Thank you, sir.
Yeah, okay.
Well, it is just a comment relating to pollution and dam safety. I cannot forget visiting one of the dams in Tamil Nadu. I came in connection with installing a power generation in a sluice, but I was shocked to see the entire reservoir was absolutely red in color, as if some blood has come in, and the canal releases were red. Absolutely. And then they later said it is releases from some viscose factory or whatever. Such things, are happening. So, and you mentioned about 8 to 12 pH value. We are facing in the northeast the opposite of it. 3 to 4 pH value. And because of that, the penstocks are getting affected very badly, and there are bursting of penstocks. So the water quality is also a very important issue. And what I feel is even the pollution control, you see, we lack coordination between departments. This pollution control department also has a large role to play relating to dam safety. Unless that happens, we are going to be living with these kind of problems. Thank you.
Actually, here I want to clarify that our dams, most of the dams which are being located in the hilly region or foot of the hills will be having low pH and low TDS. They are giving much concern as far as the lime leaching is concerned. We have already classified our dams under soft water category. We have got 7 dams out of 14 dams. Dams which are on the plains will be having high pH and high TDS.
Yeah, but the real issue, what Mr. Jaisalan pointed out remains, because this kind of an aggression is basically present in the industrial pollution, which is and many times even the urban pollution. So that is an issue which we will have to look.
Thank you, sir.
Now we will have paper number 4, the assessment, instrumentation, and management of dams, by Matthew Pavelchak. Any questions on that? We can move to the last paper, that is dam safety instrumentation with case study of Rajbal Singh. Yeah.
See, I have just 1 or 2 comments in this, not directly related to the paper, but what we are lacking in this area. See, one is related, what I have observed in the last decade, one is in this decade. Just as an example, I would like to mention, when I visited a dam under monitoring, there were files and registers of data. I just asked them, what is happening with this data? There was no answer and absolute silence. Then I said, at least can you not take the help of SAI Directorate of CWC and do something to analyze and see how best you can use this data and what comes out of it. I had a real concern on that, because I'm happy that the instruments are working. That is something, a plus point. But what is collected, how we are really making use of, that is one. And number 2 is what happened in this decade is, a dam of more than 100 meters high, the instrumentation, what has been done is miserable. There is nothing worth, reckoning as an instrumentation and use of it. Even the plumb bob was not there. Even the deflection measurement is not there. The galleries are running full, and even the pumps purchases are being delayed so badly. And now they do not know where the line is coming from, what instrumentation is installed. This happened not because of their irresponsibility, but the dam construction was delayed and delayed and delayed. The contract for instrumentation, that lapsed, and the instrument became out of date. But ultimately what we are living with is, the instrumentation has failed in that project, but how do we make good to bring about some instrumentation and make use of it? And the last comment is, the cement content, whatever is mentioned, it cannot be just replicated in another place, because we have to, have, check up with the BIS and also all the rest of it, what is required. And then there was a mention, I couldn't follow that slide, design stress and the stress measured by instrument. And it was 1/3 or something. I think that issue needs to be looked into, whether it is really should take place or there is something to be looked into. Thank you.
I think I could not get that stress data from the designers. That's why I mentioned that this data should be part of the instrumentation drawing, so that this could be put into that. As far as cement contents, there are many ingredients in the concrete, so the same thing cannot be applied to another project. I agree with you, sir. And we did that. In fact, this type of exercise should have been done just before the start of the construction of the dam, so that in our country, actually, many dams are having cracking. In US also, actually, there was a practice, when in the ACI code they have mentioned the cement content should not be more than 223 kg per cubic meter. But due to the cracking in many dams, they started having this minimum cement contents in the mass concrete. That has also been, ACI reports are very good actually on that if you refer that. Thank you, sir. Any other question?
Thank you.
Yeah, one more question.
Sir, I am from Kerala State Electricity Board. I take it as a privilege given to me to speak some words in front of the CWC chairman. See, I was attending the course throughout the day. but it seems all the papers, mostly, they are of some above the or natural way of monitoring dams. See, we are already monitoring dams with the body drain holes, foundation drain holes, then water seepage, all these things. But no paper is dealing anything about that. Usually dam is monitored in that way, I feel. Here everything is depending upon so many high-tech ways. I think this, the basic problem of these things also should be addressed. And in this specific paper, he says that by increasing the cement content to 50 kilogram per m cube, he says the strength is decreased. It is surprising. The same cement, same content of materials, you cannot expect such a value.
Well, I will respond to that. Basically, what you have raised is a thing that where, monitoring of dams and monitoring of structural behavior is a very, very vast topic. It is not possible to really compress it in a paper even. In fact, it deserves much larger examination. What you said is also correct, but then the issue here was that we wanted to get ourselves exposed to the latest technologies that are available. What new things can also be there apart from what we have been doing otherwise. So from that angle, the papers were more into that. And as far as the cement content in a mixed design is concerned, again it's a completely different topic. And there the instrumentation data can be of a supplemental use, but then there are far more other components and other issues that are at hand, which has to be done using the laboratory as well as field trials. So we will also not dwell much into the concrete mixed design because that will go out of the context in the present session. So I thank you all for having reacted very, very positively to all the papers and to all the authors of having given the very, very nice replies to all of them. I will request our co-chairman, Mr. Sureshendraji, to end this evening.
I have got a question from the author, Mr. Fukui, that is regarding the GLOF events. I would like to know whether any exercises have been conducted in Japan or anywhere else to relieve the pressure from the dam.
Yes. As far as Glacier Lake outburst flood issues, we have a collaboration in Bhutan under the support of JICA to making some field survey that's setting up such kind of monitoring station, and also providing some geophysical study like electric conductivity in the end moraine site and geophysical surveys. And after that, in the case of that project, there is a small risk at this moment in the Glacier Lake, but still combining some not only of Glacier Lake outburst flood, but also of severe weather event because of climate change. So next step, we already providing some early warning system in disaster management issues. That is one of the example situation of a Glacier Lake exercise.
Thank you very much. We had in this session some very interesting, knowledgeable and informative papers. I congratulate all the authors who have done so much of labor and brought out a number of things, particularly relating to the modernization and the modern techniques which are being employed, particularly paper number 1 and paper number 2. Besides this, I have got one problem which I have come across while having a dam safety program trip. In one of the project that is in Satiguda in Malkangiri district of Orissa, there were a lot of end hills on the downstream glacis of the dam. And this problem was not a very simple one. It was the whole slope was infested with the ant hills. What was proposed was the solution, I mean, by using the chemicals and all that. But the problem which was being faced was that probably the ant hills might penetrate the casing and disturb the filter. And that will create a difficulty in the hydraulic behavior of the earth dam. Now, what I would like to know from any of you who might have come across such a problem, and if so, then what kind of solution was utilized and to what extent? Is there any such instance?
I think if anybody has any solution or any suggestion on this aspect, I think we can take it up during the tea time. And I would request my reporter to give a few words on the session, and we close the session thereafter. Thank you very much.
Thank you. I think we had a very interesting session on looking at different monitoring systems available and integrating on large data management to have better understanding of what's happening to dams. Very quickly, very interesting presentation which was about the monitoring of the lime leaching data, linking it up with one of the projects that IIT Madras has been involved with in the last 3-4 years with the Tungabhadra Dam Board for carrying out a study on the Tungabhadra Dam using a non-destructive testing evaluation where sonic tomography was used to understand if the in-situ dam density, the density of the structural material had reduced using non-destructive testing evaluation, where sonic tomography was carried out at 8 different sections of the dam, looking at the wave velocity contours at each of the sections and drawing out correlations with the density of the cross-section at each of those sections. It would have been very interesting to see whether the lime leaching data was also available with the Tungabhadra Dam Board, a correlation of lime leaching data over time along the entire length versus the tomographic sections would have given a better understanding of where exactly grouting would be required to improve the strength of the dam itself.
Thank you. I thank all the participants and the organizers. From my side to have given me an opportunity to come here and talk to you. Thank you.
We would like to invite the chairman, Shri Ashwin Pandya, on the behalf of the organizers to give away the mementos to the presenters. Dr. Hiromichi, could you please come on the stage and receive the memento? Thank you, sir. Miss A. Topple, can you please come and receive the memento? Mr. N. Pandian. Dr. Gabriel Jimenez. Mr. Rajpal Singh. Now I'd like to invite the co-chairman to give away the memento to the chairman and to the rapporteur. Shri Suresh Chandra, sir, kindly give away the memento to the chairman. Sir, please give the memento to the reporter. Thank you everyone for your patience. Thank you. I would like to invite the chairman to give the memento to the Sorry, sir. Thank you, sir.
So before we break for the tea, I have a few small announcements to make. We'd like to have a big gratitude to our sponsors for the various events. We thank Zypex for sponsoring our workshop kits. We thank Parson for sponsoring the mementos for the delegates. We sponsor AJCAU for sponsoring the banquet dinner yesterday. We sponsor Messrs. Trimble for sponsoring the cocktails. We thank Alcofine for sponsoring the cultural program. We thank Karpi for organizing the dinner at the Mahabalipuram. And we also thank Messrs. Dimple Chemicals for putting up the stalls.